Polystyrenesulphonate nanoparticles for Spaser applications.
One of the important directions of modern
Yes, it's okay.
medicine is non-invasive diagnostics. The urgency of the problem is determined by the search of safe methods of examination techniques, from medical analysis when the patient does not feel pain, physical or emotional discomfort.
Good day, dear colleagues. Today I would like to present my work named Gold Nanorods Polystyrenesulphonate Nanoparticles for Spaser applications.
One of the important directions of modern medicine is non-invasive diagnostics. The urgency of the problem is determined by the search of safe methods of examination techniques, from medical analysis when the patient does not feel pain, physical or emotional discomfort. Fluorescence imaging and spectroscopy remain the most powerful non-invasive tools for visualization of viruses, cellular organelles, or living cells in complex biological backgrounds. However, a common drawback of fluorescent label is that their brightness is limited by optical saturation and photobleaching. As an alternative, plasmonic metal nanoparticles are very promising as optical labels with no photobleaching and low optical saturation at realistic exciting intensities, as was demonstrated in photoacoustic and photothermal sensing, imaging, and theranostics. However, plasmonic nanoparticles have wide absorption spectra and are not fluorescent, which limit their spectral selectivity and multimodal functionality respectively. Hybrid structures based on nanoparticles and fluorescent dyes are widely used for detection of different types of analytes. Various optical effects based on the amplification of electromagnetic field in the vicinity of metal nanoparticles, such as Raman scattering, increased intensity of fluorescence, can result in significant lowering the threshold limit of optical methods for the detection of small amounts of analytes. Recently, a new type of hybrid plasmonic structures known as Spaser, the acronym from surface plasmon amplification by stimulated emission of radiation, has been created. Spaser, also called nanolaser, is a quantum generator providing unprecedented efficiency as a versatile tool in nanotechnology or biomedical research and applications. The Spaser can operate in a single mode with a very high spectral density and intensity. This is due to the unique combination of intense near monochromatic stimulated emission and strongly enhanced absorption, free of optical saturation. Spacers show enormous potential in numerous applications in science, industry, and especially in healthcare because of their nanoscopic size matching those of biomolecules. This makes the Spaser one of the best multifunctional super-contrast low toxic probes in biomedical research, especially with single pulse excitation. Spaser consists of a metal nanoparticle which serves as a resonator surrounded by a thin layer of active medium. For example, fluorescing molecules such as fluorescein, rhodamine, and others, in pores of some mesoporous compounds, like silica or alumina, whose emission band overlaps with the spectrum of the mode of localized surface plasmon of gold nanoparticles. Excitation of fluorescing molecules in the spacer can be done by an external source of energy, for example a laser, leads to the accumulation of energy which is realized in the form of a flash whose brightness is substantially higher than the brightness of the best exciting fluorescent labels. In this case, the energy accumulated in the quasi-static electric field of the surface plasmon can be used in nanotechnological or biomedical applications. The use of spacer that provide much brighter glow than for example, conventional fluorescent agents for the detection of cancerous or infected cells. That can be qualitatively a new approach to the diagnosis of cancer or other diseases. To date, a few modifications of spacers have been created. However, the experimental verification of the biomedical applications of spacer is scarcely available. A few years ago, it was demonstrated that spacers might not only act as super contrast optical probes, but also effective photoacoustic and photothermal agents, which can selectively destroy the cancer cells without damaging healthy ones. This investigation shows the inspirational results as well as promising nature of the experimental approach on the one hand, and the paucity of the research in these fields on the other hand. In particular, for investigating spacer generation in a living organism, it's imperative that their generation line should be located in the transparency window of biological tissues, namely in the near-infrared region. This requires an integrated investigation ranging from adapting and optimizing these synthetic approaches to synthesize splicing nanostructures and ending with studying of spacer generation in the near-infrared range. To shift the generation peak to the near-infrared, we propose to use gold nanorods because they exhibit the plasmon resonance bond in the near-infrared range. And depending on the synthesis conditions, it can be shifted within a wide range. As it was mentioned before, colloidal core-shell splicing nanoparticles have been created, where molecules of an active medium are infiltrated into the mesoporous silica shell surrounding the gold core. The downside is that the amount of the dye involved in the spacer generation and consequently the intensity of generation is limited by the pore capacity of the silica shell. In contrast to the mesoporous silica, yolk shell particles, due to their large available volume, are outstanding alternative candidates for the spacer creation. Besides, such particles can also be used as nanoreactors or biological probes for cancer detection, which emphasize their versatility. The current dominant applied strategy to obtain yolk-shaped particles relies on the removal of a sacrificial template. This route can be described as a shell-by-shell deposition process where core shell particles are covered with an additional outer shell of an organic or inorganic material. Subsequently, the inner shell, which served as template, is removed by the dissolution with chemical agents or by heating, thereby forming yolk shell particles. Silicon dioxide is the most common sacrificial template for yolk shell particles of different types, owing to its fabrication simplicity, non-toxicity, and chemical affinity to various core materials. However, most of the current synthetic approaches involve multi-step synthetic procedures, including thermal treatment and chemical etching. Furthermore, the loading the hollow space with chemicals often requires additional processing steps, which eventually leads to a low loading. Thus, a straightforward and reproducible approach to fabricate yolk shell particles is still a challenge and highly desired. In this work, we would like to present a facile method to obtain gold nanorod containing yolk shell nanoparticles by the formation of a polystyrenesulphonate PSS shell with simultaneous hydrolysis of a previously grown sacrificial silica template in an aqueous medium. The resulting particles are extraordinarily stable in both polar and non-polar solvents and exhibit a high loading capacity for organic dyes. The gold nanorods were synthesized by the reduction of chloroauric acid with 3-aminophenol in the presence of CETA, cetyl-trimethylammonium bromide. In the next step, gold nanorods, mesoporous silica shell were fabricated by adding tetraoxysilane to the freshly synthesized gold nanorod suspension. The mesoporous silica shell, with a thickness of 35 nanometers, uniformly coats the surface of the gold nanorods with open mesoporous channels pointing radially out of the gold core. These particles are positively charged due to the remaining CETA molecules and do not undergo any visible morphological change even after several months of storage. Then the particles were coated with a thin layer of PSS, polystyrenesulphonate, a negatively charged polyelectrolyte which electrostatically interacts with the silica surface, resulting in the formation of gold nanorods, silica shell, and PSS layer on top of it. After solvent removal by centrifugation and addition of water, the sacrificial silica layer slowly hydrolyzes and it's completely removed within 48 hours. It's known that the synthesis of silica nanoparticles by sol-gel methods usually take place through incomplete hydrolysis and polycondensation of organosilane precursors. The presence of highly disordered and discontinuous CO bonds results in the formation of amorphous silica structures. Such colloidal particles, when diluted in water, can undergo hydrolysis via breaking CO networks and producing mainly orthosilicic acid until an equilibrium is established. To understand the etching process in more detail and monitor how gold nanoparticles in the shell of mesoporous silica core shell particles transform into yolk shell particles, time-dependent TM monitoring was conducted. As it can be seen in the figure, within 4 hours after centrifugation, the particles still remain their original shape and structure. At this stage, we could not clearly observe the PSS layer on the surface, which is due to the low contrast difference between silica and the polymer. 24 hours after the centrifugation, we saw that the silica particles start to destroy, and after 48 hours, as most of the silica had been already dissolved, a PSS layer with a thickness of several nanometers became visible. It should be noted that the hydrolysis process was carried out at rest, since mixing, heating or sonification led to the collapse of PSS shell. Afterwards, to enlarge the PSS shell thickness up to 15 nanometers, more polymer was added and gently mixed, and the final product can be seen here. The scheme of the entire process is depicted in this slide. When the first polymer portion is added, the PSS molecules electrostatically interact with the positively charged porous silicon dioxide surface, forming a thin layer. The distance between the molecules is large enough and therefore porous enough for the products of silica hydrolysis, mainly orthosilicic acid, orthosilicic acid, to pass through the layer. The interaction between neighboring polymer molecules is likely to be reinforced by the acid molecules situated in between PSS chain, forming a network which contributes to the stability of the shell. When more polymer is added, the PSS chain becomes embedded into the network and stuck on top of it, thereby densifying the shell. According to the dynamic scalatering measurements, the yolk shell particles are negatively charged with a hydrodynamic radius of 140 nanometers, which is in good agreement with DM data. When the particles are completely formed, they are stable in water, ethanol, DGF and other solvents. The next step was to characterize the particles. As you can see in this slide, the absorption peak, the particles exhibit two absorption peaks, the first one is around 520, corresponds to the transversive surface plasmon band of gold nanoparticles, and the peak around 840 is ascribed to longitudinal surface plasmon resonance. In comparison with gold nanorods, the second band is redshifted by about 21 nanometers due to the difference in the local dielectric constants in the surrounding medium. However, after the formation of gold nanorods PSS yolk shell structures, the band is blue shifted back from 852 to 840, resulting from the removal of the mesoporous silica shell. You can also see the FTIR spectrum of the gold nanorods, which is very similar to that of pure PSS. The XRD patterns of the gold nanoparticles show three well-resolved diffraction peaks corresponding to 111, 000 and 220 planes of the face-centered cubic metal gold with good crystallinity. Inspired by the developed synthetic approach, we elaborated a simple method to fill yolk shell particles with organic dyes. Since the removal of sacrificial silica layer was carried out in the presence of the initially thin PSS layers, we consider that these layers to be largely permeable to various molecules. Therefore, we added uranine or indocyanine green, these are two fluorescent dyes, to the nanoparticle suspension 48 hours after the start of the hydrolysis. To encapsulate the dye molecules within the yolk shell particles, we added more polymer to the suspension at various time intervals. The loading capacity of the yolk shell particles was estimated by UF with spectros, the top two spectra that you can see, of the dye supernatants obtained after centrifugation. We observed that the amount of the encapsulated dyes increased with time, as evidenced from a decrease in the intensity of the supernatant solution. It reached a maximum after 24 hours and did not change afterwards. The results of our study show that around 45% of uranine and around 70% of indocyanine was captured by the yolk shell particles. We speculate that the difference in the loading capacity can be explained by the difference in polarity of the dye molecules. Indocyanine molecules contain one beryllium, and which is positively charged, and two sulfonic groups, which are negatively charged. In purified water with a pH of 5.5, the sulfonic groups are partially protonated, which makes the molecule relatively more positively charged. Uranine molecules do not have such positively charged group, and consequently negatively charged PSS surface attracts ICG and the cyanide molecules more readily, while repelling the negatively charged uranine molecules. It should be noted that when the dyes were loaded to the stable particles, whose polymer shell was formed completely, the loading capacity did not exceed 10% in both cases. The procedure described in the present work does not require the use of any etching agents, heating, or additional chemical functionalization of the particles, which makes it very attractive from the point of view of practical applications. The two below graphs show the emission spectra of the yolk shell particles filled with uranine and ACG at the maximum loading capacity. The fluorescence intensity of the loaded particles were lowered comparing to the pure solutions of the same concentration. We assume that this fact is associated with the non-radioactive energy transfer processes arising when a metal surface is in direct contact with the fluorophore. To avoid this effect, prior to obtaining mesoporous silica shell, the gold nanorods were covered with a thin layer of ordinary dense silica, which does not undergo the hydrolysis. As you can see here, the thin shell of ordinary silica. And this silica does not undergo hydrolysis and retains its integrity within the entire synthesis processes. According to the literature, to reach the maximum of fluorescent enhancement, the optimal thickness of such initial shells should lie in the range between 7 and 15 nanometers. In our experiments, the shell thickness was around 10 nanometers. In this case, the fluorescence enhancement factor were around 2 in the case of uranine and around 5 in the case of ICG. The lower amplification factor of uranine can be explained by the lower overlapping between the transverse sulfate-plasmon bond of gold nanorods and the absorption band of the dye. Another possible explanation is that the fluorescence of molecules with a high quantum yield, close to unity, can only be amplified through the excitation rate, while the emission of less efficient emitters can be enhanced through both the excitation rate and the increase of quantum efficiency. The dye amount released from the particles after 24 hours did not exceed 10% for both fluorophores, and there was almost no release afterwards.
In summary, we proposed a facile and reliable method to obtain gold nanorods, polystyrenesulphonate yolk shell nanoparticles through the gradual formation of the polymer shell and simultaneous etching of sacrificial mesoporous silica. This approach makes it possible to charge the particles with organic dyes without using additional chemicals or etching agents. The particles have a high load capacity, exceptional stability, and a great potential for spacer applications. They can also be used for other purposes, such as the creation of biomedical probes, nanocontainers, etc. Thank you very much for your attention.